Not sure how to start. It feels weird for me to just start talking to you. I feel like I should surprise you with a fun fact. This has been haiku. Jesus, that's what I'm resorting to now.
I got my style, and it's alright.
Thank you all for joining me one last time. And thanks for watching this. I think it's important for you to see all of the things about integration by substitution that there is to see, especially for those of you who are going on to Calculus 2, where you use this technique all the time. Even in the middle of other techniques, substitution comes up a lot. And so I want you to be familiar with it. It's a powerful structure. It's a fairly simple structure, but it lets us do a lot of things with integration. So let me pick up with telling you about some of the advice, thoughts, and examples that I had prepared for you. Here's the third point I want to make. Keep an eye out for any expression and its derivative. I bring this up because sometimes it's really obvious when I should be using substitution, when I see composition with one of those math's most wanted functions, when I see an expression inside of another expression like cosine or log or e to the something, and then it really stands out. But substitution can work in moments where it doesn't necessarily look like there's really composition. There probably still is, but you can use a substitution more than you might think, and so I want to draw your attention to some scenarios where it may not look like I necessarily have a composition per se, but when I have an expression and its derivative, I might still be able to pull it off. Here is an example. Let's evaluate this integral of sine squared of x times the cosine of x dx. Now, when you look at this, it doesn't really necessarily look like you've got composition, but I do see something and its derivative, right? I see sine and cosine, and sine has a derivative of cosine. Now, there actually is composition here because sine is inside of the polynomial x squared, right? If I take sine of x and put it in x squared, I get sine squared of x. So there is actually composition, but it's not immediately obvious that's what's going on. But because I see an expression and its derivative, that's what gets some of my wheels turning thinking about a substitution. And so here I can pull that substitution off. I'll choose u to be sine of x, so that du is cosine of x dx. And with that, my integral just becomes the integral of u squared du. Well, that's pretty easy to integrate. I'll just use the power rule to give me u cubed over 3. Of course, I do need that plus c, which always comes in. That one sounded painful. Jeez. And when I sub back, remembering that u is sine of x, that becomes sine cubed of x over 3 plus c, and that's my answer. Let's try another one. Here's the integral of 1 over x times the natural log of x dx. There's a lot going on in here. Once again, you might not see composition per se, right? There's nothing, fancy inside of the logarithm. But I do have an expression, natural log of x, and its derivative, 1 over x. And because I have both of those things, I might try my hand at a substitution, where I let u be the big expression, so the du will be its derivative. And here that actually works. If I make my substitution here, u equals natural log of x, then du, the derivative, is 1 over x dx. At which point I've just got 1 over u du. And I can integrate this. I know that integral as well. That's just the natural log of u plus c. Goodness. And my u, remember, is the natural log of x, so I get the natural log of x plus c. something I'm sure you're just real excited to be part of. But that is the answer. That is all that there is to do it. The actual integration here isn't difficult. It's spotting those substitutions that takes a little bit of practice and getting used to. Here's an opportunity for you. Try it with a buddy, or try it on your own. Hey, you know what? Go ahead, find classmates, get together, make a day of it, and integrate e to the x secant squared of e to the x dx. You should get tangent of e to the x plus c. Your choice of u would be e to the x, and then du is also e to the x dx, at which point you get just secant squared of u du, and we know the antiderivative of secant squared is tangent, so that all works out just lovely. Here's my next point. You might have to manipulate the expression to see it. These are some of the hardest to spot, I think. And again, this comes with a lot of practice, but I want you to see a few, especially those of you going on to Calc 2, where as you're building up the techniques that are going to let you solve integrals, this is a technique that you're going to want to get good at. There's a number of times where I get an integral and I can't immediately do anything with it, but I'm in the habit of recognizing what kind of structures are going to be useful to me, what kind of things I can change and manipulate so that I will be able to do a substitution or one of the other techniques that we're going to see. So yeah, having to manipulate the expression to be able to get it to a place where you can use a substitution, that can be hard to spot. But let me show you some examples and tell you what I see in those examples that makes me think about a substitution even before I start manipulating. Have a look at this one. Here's dx over 16 plus x squared. So, what do I see in here? Because at the moment, there's nothing really that stands out. This is not just an integral I know. I don't see composition. I don't see an expression and its derivative, but I do see something that looks kind of like the derivative of arctangent, and that's what gets my wheels turning here. I may not have an integral that I immediately know, but I have something close to something that I know. And that's one of the big takeaways that I want you to get out of this point here is when I'm looking at this integral, no, I don't know how to do it immediately, right? But I'm looking at it and it's reminding me of something that I do know how to do. I do know how to do the integral of 1 plus x squared. Is there a way that I could manipulate this so that I could get it to look more like that, or at least into a form where I think I could pull some kind of a substitution off? Well, the big thing with arctangent is it needs to be like 1 plus x squared. And, you know, the variable, I can work around that. I might be able to do a substitution that makes, you know, it's something else squared, right? But the 16 has got to go. And so the first move that I'm going to make here is I'm actually going to pull a 16 out of everything in the denominator, which at first seems like a very unfortunate choice to make in this life. But when I do, the reason that I'm doing that is because now I'm left with something that looks a little bit more like what I need it to. I've got this 1 plus x squared over 16, and that 1 is pretty crucial. With that, I can pull the 1 over 16 out of the integral, and now in the bottom I'm left with 1 plus x squared over 16. Well, keep in mind, the expression that I've got here, I'm trying to get this to look like the derivative of arctangent, which is typically 1 over 1 plus x squared. But now I've got it in this format of like 1 over 1 plus something squared. By the way, I want to draw attention to the fact that, yeah, the dx here is on top. It has been since the beginning, but I mean, that's no different from just having it multiplied over here, right? But sometimes we'll put it up here just to save a little bit of space, and hey, if there's nothing else up there, might as well. If I take this expression, I can rethink of this as being dx over 1 plus x over 4 squared. It's something squared. And now we're in a good spot, because now after manipulating it, I think it's a little bit more apparent that I've got composition with one of my math's most wanted functions, right? With one of those integrals that I actually know how to solve. So let me say it like this. When I saw the original question, there wasn't much I could do. So my goal at that point became to try to manipulate it so that it would look like an expression that I would know what to do with it. And because the original expression reminded me of the derivative of arctangent, my goal became, hey, can I change the way that my expression looks so that now it will be composition with that math's most wanted integral? Can I rewrite it so that it will be something that I can use a substitution on, something where there is composition with an expression that I know how to integrate? And now I'm in a good spot, because I see this x over 4 is inside this 1 over 1 plus something squared, and I've got the expression and its derivative. It only differs by a constant. I should be good from here. The choice I'll make for my substitution is the thing that's inside, x over 4. The derivative du is 1/4 dx. Here I'm going to use that second technique that we talked about, where I'm going to multiply both sides of this equation by the 4 so that I'll just get the dx by itself. That means that 4 du is equal to dx. That means that now I can swap out that dx for 4 du, and I can pull that 4 right out of the integral like before. And when I'm done, I'll have an expression that's entirely just in terms of u. I'll pull that 4 out. That's going to be 4 over 16 is 1/4. And now I've got du over 1 plus u squared, or in other words, 1 over 1 plus u squared times du. I know that integral. It's arctangent. The arctangent of u plus c. That's probably my favorite. Now I can sub back. Remember that u is x over 4. So I get 1/4 times the arctangent of x over 4 plus c. And that's my answer. That kind of manipulation is vital, crucial even, and it gives us a way of being able to take antiderivatives of things that look like our arctrig expressions. And so I want to summarize kind of the 3 of those with this theorem. All 3 of our major arctrig things have antiderivatives that look very similar to each other. So if I see anything squared plus x squared, I can use this rule now to make it 1 over a arctangent of x over a. In our previous example, a was 4, because 4 squared is 16. So when from now on, when I see like 1 over 16 plus x squared, I can say, oh, well, that's 4 squared, so I'll put it as 1 over 4 and then x over 4. And the same goes for arcsine if I see a squared minus x squared under a square root, or arcsecant if I see it like this. I want to point out that a does not have to be a perfect square. So if I saw like 1 over 3 plus x squared, I would write that as 1 over the square root of 3 arctangent of x over the square root of 3. Fifth thing here, you don't always need substitution. This goes back to some things that I was saying in class the other day, like that old saying, right? When all you have is a hammer, everything looks like a nail. And even now, the only tool that you've got right now is substitution, and so every integral that you look at, that's all you think about, right? You're in a section on substitution, and if that's the only tool that you have, then every integral that you look at, you're just going to be like, substitution, right? But not everything needs a hammer, and not every integral needs substitution. So I want to encourage you to keep your eyes peeled for times when you need it and times when you don't, because there's situations where you might be able to pull off a substitution, but it might have been a lot easier if you just hadn't. God, should I fix this? Here's an example. Have a look at this integral x squared minus 5x plus 6 over the square root of x. Now, my guess is that when you look at this, you don't immediately think substitution, and that's not a bad thing, necessarily. There is a way to do this with substitution, but it requires a little bit of cleverness. And so, I mean, it's possible, right? Here's what I'm seeing, right? I see a square root. I see a square root of x. I know that the derivative of the square root of x is 1 over 2 root x. Now the problem there is I don't see this and its derivative. It's just a square root of x kind of like is its own derivative. Anyway, it's in the denominator, right? But the way that I'd be able to pull this off with substitution would be to say, okay, if I let u be the square root of x, then this would be part of the du, and everything else I can actually write in terms of the square root of x, because x is the square root of x squared, and x squared is the square root of x to the 4th. So I could pull this off. I could say that the substitution I'll make here would be that u is the square root of x, and then du is 1 over 2 root x dx. Granted, I don't have the 2, but I can easily adjust constants. Well, that wasn't on time. Down here, I'll multiply the 2 on the outside and in the denominator, so 2 over 2 to make everything work there. And with that, I can now make a substitution and say, yeah, this actually works out perfectly for me. I get x squared is u to the 4th, x is u squared, and, well, 6 is just 6. And then the 1 over 2 root x dx is my du. And from here, I could pull this off. I could use the power rule, add c. Yeah, and then substitute back, right? I can change that back for the square root of x. I mean, simplifying here, right? If I wanted to make this a little bit cleaner, I could write the square root of x as being x to the 1/2. At which point I would get, x to the 1/2 to the 5th, power to a power. I'd multiply exponents, and I'd get 5 halves and 3 halves, and I might as well change that to 1/2 so it doesn't look out of place. But now that's an interesting thing. If I can write the square root of x as x to the 1/2, maybe I could have just done that from the beginning and saved myself the trouble. Let's look at this example again. If I were to take this expression and rethink of this as being x to the 1/2 in the bottom, I could use my exponent rules and say, oh yeah, I've got the same base, x over x. I could split it up over the addition and subtraction. In each case, then I'd say, okay, x to the 2nd over x to the 1/2, bases are the same, subtract exponents. 2 minus 1/2 is 3 halves, 1 minus 1/2 is 1/2, and 0 minus 1/2 is negative 1/2. And now I get an integral where I can just use the power rule. And I just get exactly the same thing. Here, this goes up to 5 halves. When I divide by 5 halves, that's the same as multiplying by 2/5, so I get 2/5. Here, this goes up to 3 halves, which I would then need to multiply by 2/3, times the 5 gives me 10/3. And then this goes up to positive 1/2. When I divide by 1/2, that's multiplying by 2, giving me 12, and it's exactly the same expression that I would have gotten before, no substitution necessary. So my point here is, yeah, I mean, keep your eyes peeled for substitutions, but if you can find an easier way to do an integral, then yeah, do it that way. Point number 6 that I want to make. Substitution actually gives us integrals for some of our basic trig functions. Right now we've got the integral for sine and cosine, but we haven't yet discussed an integral of tangent. But with the tool of substitution, we can actually find one. It's pretty adorable. Keep in mind, tangent is just sine over cosine. Oh, and would you look at that, I've got an expression and its derivative. Now here's the problem. If I were to choose u to be sine so that du is cosine, then my du would be in the denominator. That doesn't work. Du has to be like in the numerator. It can't be on the bottom of anything. But fortunately, it works both ways. If I let u be cosine, then du would be negative sine, and I'd get everything that I need. I'll do that for my substitution. I'll let u be cosine, so that du is negative sine dx. I'll have to adjust for that negative. When I multiply the inside and outside by -1, I end up with just this integral of -1 over u du. And that's definitely natural log, right? So it'll be negative natural log of the absolute value of u plus c. And then when I sub back to the u being cosine of x, I get just negative natural log of the cosine of x plus c. Most people leave it like this, but if you're ambitious, you could make the observation that this negative out in front, thanks to a log rule, could be pulled inside to be an exponent and call this cosine to the -1 power. Well, since cosine to the -1, that's the reciprocal of cosine, so that would be 1 over cosine, which is secant, so you could call this the natural log of secant of x plus c. Most people don't do that. I usually just write it like I have it here in purple, but hey, if you don't like negatives and you like secant, then hey, that's the answer for you. Here's the other big one we've got, and that's secant. What would be the integral of secant? This, oh, you're going to love this. This is absolutely adorable. You're going to look at this and say, I would not have thought of this in a million years, and I wouldn't have either, but it is so neat how we can do this. I'm not going to rewrite secant as 1 over cosine. I've actually got a better trick in mind. And so here's secant of x. Here's what I'm going to do. I'm going to multiply by a fancy form of 1, secant x plus tangent x over secant x plus tangent x. That is 1. So this is allowed. I have not changed the value of the expression. And if I distribute secant is times all of this, right? So if I were to multiply it out, I would take my secant and distribute it to each piece on top. Just the top. Just the top. And that would give me secant squared of x plus secant x tangent x all over secant of x plus tangent of x. And it's the most beautiful and phenomenal thing that could possibly have happened here. Now I can actually do a substitution if I let u be secant x plus tangent x, the expression in the bottom. Because if I take the derivative of this, well, the derivative of secant is secant tangent, and the derivative of tangent is secant squared. So it doesn't actually, it works out perfectly. Because I add in whatever order I want, right? So it's like the derivative of this ends up being this piece, the derivative of this ends up being this piece, but everything just works out so perfectly. This ends up being just the integral of du over u, which is, again, the natural log of u plus c. And subbing u back to be secant x plus tangent x gives me the integral of secant. So now we've got those. I want to point out that some integrals require multiple methods, and now we're getting into the thick of it. Sometimes we'll need more than one u substitution, or we might need some other technique that you'll learn in Calc 2. But I feel like this is as good a time as any to introduce you to really our first brain buster. Have a look at this absolute adventure of an integral with me. The integral of 2x plus 3 over x squared plus 6x plus 10 dx. I'm going to take you through my solution of this integral, and probably most of the way you're going to be thinking, what, why, or how would you know to do that? And I'm going to come back to this at the beginning and tell you about what I saw and what made me think about this, because this is actually kind of a common technique that we end up seeing. Here's what I'm going to do. I'm gonna take this integral and I'm gonna split it up in the most adorable way. Here's what I'm noticing. I'm noticing I've got this quadratic on the bottom and I've got a linear on top, which has got the wheels turning for maybe some kind of a u substitution, because I've got an expression and its derivative, but it's not exactly, right? The derivative of the bottom would be 2x plus 6, and I've got 2x plus 3. So here's what I'm going to do. I'm going to split up my integral in the most adorable way. I'm going to rewrite the top as being 2x plus 6, the derivative of the bottom, minus 3. 6 minus 3 is 3, so I wouldn't be changing the expression. I would just be writing it in a new way and then splitting it up like that. So now I've got two integrals to solve, which feels way worse and arguable. But now over here, I feel good about this integral, because here I've got the bottom is this expression and the top is its derivative. And over here I won't be able to do that, but I can break it up in pieces. And with this expression, I can just straight up do that substitution. I'm going to let u be x squared plus 6x plus 10, so that du is 2x plus 6, and rather than go through the whole thing of showing you that it's, 1 over u du, I feel like we've seen this enough that I can do this one pretty quick. So here's the quick version. This ends up just being the natural log of x squared plus 6x plus 10. And we're halfway done, right? I've got that one taken care of. Now we've just got this integral to figure out, right? But looking at this one, okay, I've got just a constant on top, and I've got the quadratic in the bottom, which has, I don't know, an aura of arctangent, but it doesn't quite look anything like arctangent, so we're gonna need to do some manipulating. But yeah, I'm gonna look at this expression now. I'm gonna pull that 3 out, so that now I've got just the 1 over the quadratic, which feels better. And now I need to get the bottom to look like that arctangent thing, which is usually just like 1 plus something squared. Well, I can actually do that here. I'm gonna peel a 1 off of this 10. And that's going to make it 1 plus 9. So now I've got the 1, and this actually is something squared. This is, if I were to factor this, that would just be x plus 3 squared. And this is that arctangent form. I've got 1 over 1 plus something squared. I can do a substitution here. Very simply, u is going to be x plus 3, and du is just dx. Which means I end up with 1 over u squared plus 1 du, which is the arctangent of u, plus c. When I sub back, that gives me the arctangent of x plus 3, and at this point I've got the whole integral. I've got everything that I need. Everything is solved. I broke it up into those two pieces, and that got me the rest of the way. This is actually a pretty common move that we have, and you might talk more about this in Calc 2 if you go on to take Calc 2. Whenever I've got like a polynomial, like a quadratic in the bottom and a linear on top, which does come up with some level of frequency, this is usually the way I go about it. I rewrite the top and then break it up so that I can do a simple natural log u sub with part of it and an arctangent u sub with the other part. All those together give us our answer. Here's one for you to try. Also a kind of a mixed methods over here, but yeah, go ahead and buddy up with anybody who happens to be in your vicinity, and pause the video here and give it a whirl. Using the same kind of practices we just did, you should get the square root of 16 minus x squared plus 4 times the arc sine of x over 4. Good times, I'm sure. Here's the last point I want to make. With a definite integral, you can choose to change back or not. With the definite integral, we've got the limits on, the upper and lower limits that we have to evaluate our expression at. And if we want, we could set that up to just do the integral with u and not have to change back to x. I want to show you what I mean with this example. Have a look at this gem. The integral from 1 to e on the cosine of pi times the natural log of x over x dx. Yeah, Chris, I thought you might just really appreciate that e. Have a look at this with me, right? So I'm already thinking substitution because I see composition. I see something inside of my cosine. I see this natural log and its derivative, 1 over x. So I'm definitely feeling the vibes of a substitution, where my u will be that inside piece, the pi times the natural log of x. And if that's the case, then du would be pi over x dx. Remember, pi is a constant, so it would be pi times 1 over x. Now, when it comes time to substitute this, I'll need to multiply inside and out. I need to by pi over pi in order to make everything work out with the constants. But now when I want to actually plug that u in, well, you'd love to just write 1 over pi times the integral of 1 to e cosine of u du, but that's actually not true. And the reason it's not true is because these limits, the 1 and the e, those were values of x. But now we got rid of x and we've placed u. And so this is suggesting that u is going from 1 to e because I'm integrating with respect to u, and that's just not true. So we've got a couple of ways to proceed from here. One would be to say, hey, I'm going to look at this 1 and the e, and I'm going to change the limits of my integral so that instead of being in terms of x, they'll be in terms of u. Well, when x equals 1, u would be pi times the natural log of 1. Natural log of 1 is 0, so u would be 0. And when x is equal to e, well, then u would be pi times the natural log of e, which is pi, since the natural log of e is 1. And so here I'm just working out what the values of u would be when x is each of its limits. So if we go this way, we can say, oh, this is great. I'll just change the values. I'll just change the limits on my integral to be, instead of being in terms of x, now they're in terms of u. Because as x goes from 1 to e, u, equal to pi natural log of x, goes from 0 to pi. And now I can just carry out as normal. When I integrate, I get the sine of u, and now that it's a definite integral, I have to go from 0 to pi. Because I changed the limits, I don't need to sub back. I can just plug them in and say, yeah, I get u equals pi and u equals 0. I'll plug both of those things in. Both of those are 0, so I end up with just 0. And this works great. We get to just plug everything in for u and not give x a second thought. But there are occasionally times when I would rather sub back than have to figure out things with u. Maybe my u is just a really wild substitution, and I'm actually looking forward to getting it back in terms of x. And if that's the case, here's the way I could write it. I could just say, instead of swapping all of my limits to be in terms of u, I'll just write x equals 1 and x equals e up here. That way everything that I'm saying is still true. I'm not indicating that u is going from 1 to e. I'm acknowledging that these are still x values. And then I'll carry on my merry way. After I integrate and get the sine of u, then I'll sub back and say, yeah, u is pi natural log of x, and now it's safe for me to take this from 1 to e. And you'll still get 0 just like before. It is 0, by the way. If you look at the function between 1 and e, it actually is above the x-axis the same amount of area as it is below the x-axis, and it perfectly balances out in both. That's all I've got for my notes in this section. Is there more to say? Yeah, probably. Have I already said too much? Absolutely. I mean, we could keep talking. We could go through more examples. We could talk about times when you need to do more than one substitution in order to pull things off. But I don't feel the need to do that. I feel like you've already gotten a pretty good picture of what substitution can look like and what you can do with it. Thanks for joining me with this, and thanks for joining me all semester. I've really enjoyed teaching you guys in both of my calculus classes. You guys have just been a lot of fun, and I'm so glad that I got to share one more thing with you. Have a very restful weekend. Prep for the final, and I'm here if you need me. Take care.